Hello, thank you for clicking on this video. Today I want to talk to you about going to Mars. This video will be focusing on the orbital mechanics that is required to go to Mars, and we will be split up into two main parts, Hohmann transfers and capture velocities. But before we go into that, let's go back and talk about orbits. Now, looking at this orbit, I would like to label it by naming the lowest point on the orbit as the perigee and the highest point as the apogee. Furthermore, since there are many different types of orbits, I'm interested in something called eccentricity, which we can define as the radius of the apogee minus the radius of the perigee divided by the radius of the apogee plus the radius of the perigee. The eccentricity is vital for determining the shape of the orbit. Take a look at these different orbits. Notice how the eccentricity of the orbit changes as the shape of the orbit changes. This may not seem necessary right now, however, later on it will become very important and necessary for our calculations. Next, the apogee and perigee are added together and divided by 2, which gives us something called the semi-major axis. This is an extremely important term in orbital mechanics and shows up in nearly every equation there is. Now I want to introduce to you some formulas about orbits. The first one is called the vis-a-vis equation. It is v squared equals to mu times 2 divided by the current position minus 1 over the semi-major axis. This equation will become extremely important when we are doing orbital maneuvers in the orbit itself. For example, if I am in a circular orbit 200 kilometers above the Earth and I am moving at a speed of 7,785.86 meters per second. However, if I want to get to a different orbit, one such where my apogee is 300 kilometers, how much extra velocity must I gain to get to that altitude? Well, the change in velocity would be the velocity at this point r1 minus the velocity at this point r2. Luckily, we can work it out. We have this amazing equation which can work this out for us. This will be extremely useful in later stages of our mission. Now I will talk about escape velocity. Escape velocity is the velocity that is required to leave a planetary system. If I want to leave Earth, for example. The general equation for escape velocity is the square root of 2gm over r. Gm is usually simplified to mu, and that is what is used in the vis-a-vis equation for those people who are confused. We can work this out, and the escape velocity for Earth is at 200 kilometers, which works out to be 11.01 kilometers per second. That is insanely fast, but we can go even further. Suppose we are at the point infinity and we want to calculate our velocity. Well, let's work that out. We can see that for velocity at point infinity, it's going to be negative mu over r. We can't use this in any real computation, but it would be useful to derive another formula. If we consider our velocity at point r, vr, then with some algebra, can become vr squared is equal to be v escape squared plus v infinity squared. This is going to be extremely useful later on. Another concept that is required for you to understand is angular momentum and energy. These are quite simple topics, however, their power should not be underestimated. Angular momentum is simply like linear momentum. The rules are the same. For orbits, angular momentum is the same when 2 points are 180 degrees away from each other. The formula for angular momentum is L, don't ask why it's L, is equal to mass times the velocity times the distance from the body. The other concept has been visited before. It's energy, and was touched upon in the first video. One thing to know is that energy is always conserved within an orbit. There is no point where there is more or less energy at a certain place unless extra energy is added, like when a rocket ignites its engine. Now, to get to Mars, we have to go through something called a transfer orbit. A transfer orbit is when we coast towards Mars by adding a little bit of energy. That we can call delta V1. To get into a Mars orbit, we have to add a little bit more energy, and we can call this delta V2. Vp is the velocity at the perigee of the transfer orbit and can be expressed as Vp is equal to v1 plus delta v. v2 is the velocity at the apogee of the transfer orbit and can be expressed as v2 is equal to va plus delta v2. Great, let's just get all the equations up and then we can start to discuss our transfer orbits to Mars. First, let's try and write va, which is the velocity at apogee of the transfer orbit in terms of vp. There, we can already have a way to write it down. Just use the equations of angular momentum. Now we can substitute this into the equation and the energy equation and rearrange the factor. With a little bit of algebra, we can essentially boil this equation down to Vp is equal to the square root of 2 mu times R1 divided by R1 times R1 over R plus R2. Using this and the first equation, then we can get that delta V2 is equal to root mu over R2 times 1 minus root 2 R1 divided by R1 plus R2. These two expressions are the one that we are interested in and will turn out to be useful. Now let's suppose that we are in an orbit that is 250 kilometers above the Earth. We need to ask ourselves, what is the extra delta V that is required to get ourselves into an orbit, Mars transfer orbit? Well, we can use the equation Vr squared is equal to V infinity squared plus V escape squared. In this situation, V infinity is always equal to V1, and this can be extremely useful because now we have to do some actual math. Using the values that can be crunched out, we can see that Vr is going to become 3.6 kilometers per second. This means we have to speed up 3.6 kilometers per second to get to an orbit on Mars. Now, the question is, where do we have to do this? The way to understand this is by calculating the angle of the burn after we cross the perigee of Earth's orbit. Luckily for us, there's a nice little equation that does this for us, and the equation is cosine inverse of 1 over the eccentricity. Eccentricity can also be expressed as 1 plus Rp times V infinity squared over mu. This means, after some number crunching, that the angle of the burn would be at 30.09 degrees after the perigee. Okay, so now we're on our ways to Mars. Great. How are we going to stop? Well, this is something called capture velocity, which is something that is exactly what it sounds. Capture velocity is how much velocity is required to get our spaceship into Mars orbit. Well, how much is it? It is exactly delta V2. How great is that? So let's put it in the numbers and we get 2.648 kilometers per second to slow down. And assuming we want 250 kilometers orbit above Mars surface, that means our periapse angle relative to the Mars velocity vector would be 50.258 degrees. And we're done. We have successfully sent an object to Mars with all the realistic math. And remember, this is exactly what they do in space organizations like NASA. So thank you for being a part of this journey with me. And remember, keep looking up.